I promised the people who couldn't be here that I would record, so I got to remember to actually hit that. Okay. We're going to be looking at specifically significant digits in terms of what is that telling you about data that you collect. This is going to affect every assignment, every math problem, every experiment, everything that we do through the whole year, which is part of the reason I spend a fair amount of time on this early in the year, because it does have a trickle-down effect all the way down, because you can do everything right within the problem, but if you're not following the proper significant digits protocols, you can get an answer that's actually very, very different. And you're going to see some of that today with a few of the little examples that I gave you. And you'll see it more as the year goes on. So let's talk about when they are used. Anytime that you're making a measurement, and particularly a measurement for data collection. If you're doing qualitative measurements, obviously, significant digits is not necessary, but anytime you're making quantitative measurements, this is going to be important, all right? They indicate how precise your measuring tool is, and this communicates to other scientists and other people who are looking at your data what tool you used and what they should use as a result in order to replicate your experiment. So it's used for validity, and it's also used to hold you accountable when people try to replicate your experiment. It's also good for you to realize, okay, what are the limitations of the tools that I'm being asked to use? Specifically when we go to like doing the regional labs and stuff, where you're doing a lot of measuring type things, or as we do labs throughout the year, as you go through and do measurement type, lab activities, you're going to notice that depending on what you have available to you, that's going to really change your results. And then the more calculations that you do down the line, the more and more that will affect what you're able to produce as a result. They also indicate how specific your results to mathematical models can be, which you've heard me use this phrase, mathematical models, before. If you remember from our last Zoom session, we talked a little bit about how the point of physics is not the math, but math is used to describe what we're seeing. Okay, that description, that descriptive element of it is a mathematical model. All right, so like for example, the velocity equation or acceleration equations, or the graphs that we draw from watching an object move across the floor. These are giving us mathematical models to be able to then predict what's going to happen if should we change a variable. And so significant digits will affect how accurately those models can model what we're seeing and what we can expect as a result from them. So that's a whole lot of really fancy talk for basically the idea is that significant digits tells us how good your ruler is. So one of the hardest parts for a lot of people is knowing where and how to round when they're measuring. Most of us have been measuring since we were in kindergarten, but we never give any thought to the type of ruler or the type of tool that we use for measuring, let alone then how does that affect where we can round our numbers. So when you're measuring something, you have to go to the smallest unit your measuring tool has. Get your value down to that point and then estimate one place past that point, and that will be the final digit that you write down. And that's where people fall down. They're with me through, if you look at our example here, they can see the line. They can see that the line is 3 centimeters and 8 millimeters long. They can see that, and what they want to write is 3.8. What that communicates to other scientists, however, is that your ruler doesn't have any millimeter markings. That's what that communicates. So in order to tell other people that your ruler had millimeter markings, we have to go, okay, is the point of that ruler exactly on the 8? Is it a little bit past the 8? Where is it? So in this case, I tried as closely as possible to get it exactly on the 8 millimeter line. What we can then do is estimate that last digit. And that then communicates to everybody else down the line, not only did my ruler have millimeter measurements, but I know that the end of the arrow or the end of the object I'm measuring is exactly on that 8 millimeter line. And so the measurement would actually be 3.80 centimeters if you have the correct precision. Does everybody understand what I'm talking about there when I talk about this idea of estimating that last place? Yeah? Okay, sorry, your thumbnail is very, very small, so it's hard for me to see nods here. So if it was a little bit past the 8 millimeter mark, which happens, what we would then do is we would estimate that last digit. And more often than not, what you'll see is people will estimate to usually a 0.5 millimeter. So they'll say 3.85. You won't usually see a lot of 3.83 or 3.89 unless the distance between those values is very, very large, so that it's easier to see. As you can tell from our diagram here, the distance between millimeter markings on a ruler is very, very small. And so we will not be able to actually say with any confidence, oh, well, it's closer to the 9 or it's closer to the 8. So we just kind of hit the middle mark and say 3.85 because it is just an estimate. And so you have to, all it's doing is it's sending a signal saying, we have the millimeter markings, we're a little bit past that 8 millimeter mark. So that's how you determine how many significant digits you should have when you measure. So anytime that you take a measurement in lab, you need to look at your ruler, look at your stopwatch, look at your what have you, and then go, okay, how far can this thing measure? How accurately can we do this here? And then go one place past that and use those zeros or use those estimated numbers as an indication of, okay, are we exactly on the mark or are we a little bit past? How confident am I in these numbers? So that you're communicating clearly to the next people down the line. So here's the nitty-gritty, and this is usually where, and for years, this is how I taught it. I would start teaching significant digits by teaching the rules, which is awesome and great and wonderful. But it doesn't really give you a lot of indication of why we do significant digits. All right. And that's part of the reason why I've kind of changed how I've taught this over the years. And I try in an effort to sit there and go, okay, this is what we're trying to do with these numbers. But the rules are pretty straightforward. Anytime you've got a digit between 1 and 9, that's considered significant. So if you've got the number 145, it has 3 digits, it's like 4 and 5. Everybody can do that part. The problem is the zeros. All right, the zeros are the tricky parts. All right, if you've got a 0 between what I call real numbers, the 1 through 9 numbers, between 2 real numbers, that 0 is significant. Okay, it's there for a reason. It's saying, okay, we don't have anything in that 10 spot. We don't have anything in that 1 spot. But it still has significance in the measurement. So for example, 408 has 3 digits, 4, 0, and 8. All right, the problem comes with decimal points. The placement of your decimal point will affect how the zeros at either the end or the beginning of a number are considered. All right, and I never realized when we did decimals in elementary school that this is actually what decimals are used for. I had no idea. I understand now that that's a part of what decimals do, is they indicate certainty. If there is a decimal in your number, then the zeros are significant. So for example, the number 130.0 has 4 digits. All right, 1, 3, 0, and then the 0 after the decimal point. That decimal point says, I am absolutely certain that my object is 130 meters long. And I am certain that it ends exactly on the line. The number 130 with just the decimal point has 3 digits, although you'll very rarely ever see it written this way. But it does happen. So that decimal point makes that 0 significant. So that's saying, okay, my ruler has hundreds and it has the tens. I don't have the ones placed, but I am exactly on 30. And so I know that that 0, that represents being exactly on the line, and therefore it is significant. If you have a number that's less than 1, the zeros in front of the number are not significant. Any trailing zeros will be. So for example, 0.00240 only has 3 digits. This is the number one thing people miss when they do significant digits on problems. The number one thing is they want to count those zeros in front, and they don't count the ones behind, when in fact the opposite is true. The 2, the 4, and the trailing 0 are the ones that count. And this leads us into our conversation about placeholders. A good rule of thumb is a 0 will be considered significant if we could take it out of the number and still have the same value of the number. The number 130 and the number 130.0 has the same value. So the zeros must be there for a reason. All right, this doesn't work in every situation, but it is a decent rule of thumb. If you can take it out and the number is still the same, it's significant that it's still there. If the number would be a different number without the zeros, then they are not significant. They're what are called placeholders. They're bumping your numbers up to the proper place division. So 130 and 13 are obviously different numbers. So the 0 is acting as the placeholder to bump the 1 and the 3 up to the proper place. Therefore, the 0 is not significant. All right. This was, you know, they have all kinds of fancy mnemonic rules. They have all kinds of fun little games that you can play with going towards the Pacific or the Atlantic Ocean, da-da-da-da-da. They have all kinds of fun things, but this is a good rule of thumb. Everybody's got the 1 through 9 rule. The problem is what to do about the zeros. If you can take it out, it must be there for a reason. If you can't take it out, it doesn't count. So in our previous example of 0.00240, those first 2 zeros, if we took them out, we'd have a different number. But that last one, it wouldn't change the number if we dropped it off. So that last one is significant and the first 2 are not. Does that make sense, how I've explained that idea of if you can remove it, it's supposed to be there? That's something I've kind of picked up over the years that some people have found to be a little bit confusing or found to be really helpful. It's very binary. So let's do a little bit of kind of practice here. And once again, if you're wanting to take a look at these rules again, or if you're wanting to go over, you know, some of these examples again, feel free to let me know and I can email you a copy of the PowerPoint. Let's look at some numerical examples and run a few examples. So if we have the number 439, how many significant digits does that number have?
3.
3, obviously. Like I said, nobody ever has problems with those. Number 5003, however, how many does that one have?
4.
4. Very good. Those zeros in between count. 5.00. This is where people start to miss the problems.
3. Yeah. 3.
3. Those zeros could be taken out, and therefore they have to be there for a reason. We included them for a purpose. 0.004. 1. Any numbers in front of your decimal point don't count unless you've got a number there in the front. If it was 1.004, then we would go back to that rule number 2, wouldn't we? Where it's in between 2 real numbers. That's a different problem. The number 1,000. 1. Notice there's no decimal point. If I would have said 1,000 decimal point, that would have had 4. So you need to look very carefully to make sure that there's not a decimal point. And if you're not certain, if for some reason you have a problem and you can't really tell if there's supposed to be a decimal point there or not, you need to ask because it makes a big difference. All right, and then the last one, 0.03400. 4. Right. Preceding zeros don't count, but the final ones are there for a purpose because they could drop off and you'd have the same number. Good. Oh, I gotta hold on just a moment. Oh, it's one minute. There we go. Let's look at some mathematics with significant digits. Once people have the rules figured out for how to determine how many are in a number, this is the second part where they really struggle. How to actually do mathematics. And this is where it's going to most impact your life going forward because like I said, every problem we're going to do is going to involve, you know, solving the number of significant digits and then calculating with that. The basic rule of thumb here is that your answer to a math problem can never have more significant digits than the least precise number in the problem. So your worst measurement is going to determine how good your answer can be. Which is also why in group work you have to make very, very certain that everybody is measuring the same way. Because if you've got one person who's not paying attention and he just throws a piece of data at you, that's going to be what determines how well your results come out. So the least precise number in your problem will tell you where you have to round to. So we have 2 sets of rules. We have the rules for multiplication and division, the rules for addition and subtraction. For multiplication and division, you figure out the number of digits in each of your numbers in the problem, and then you round to the fewest number of significant digits. Most people feel this is easier. So for example, if we have 439 times 0.01 times 4,500, what you get as an answer is 19,755. 439 has 3 digits, 0.01 has 1 digit, 4500 has 2. So our answer can only have one significant digit. That means 19,755 becomes 20,000. And the more calculations you do, the bigger that discrepancy gets. So you can begin to see, like, look at how much difference there is in just this one problem. Imagine how much more if you're doing 2, 3, 4 sets of calculations where you're using the answer from the previous problem to get the answer to the next problem. Because you're going to lose 300. In this case, you would lose 300 everywhere along the line. It would exponentially become a bigger and bigger problem, even for a very small difference in measurements. Addition and subtraction, most people feel are a little more complicated. It's just different. And please do not get them confused. If you have a problem where you have multiplication or division and addition and subtraction, then you need to use the order of operations to figure out where you should round. In addition and subtraction, your answer must be rounded to the least precise place value. So for example, if I have 45.12 plus 0.004 plus 35, that makes 80.124. 45.12 goes to the hundredths place. 0.004 goes to the thousandths, so even though it's the smallest number, it's the most precise. 35 goes to the ones. So our answer has to get rounded to the ones spot. So 80.124 becomes 80. In this particular case, it's less of a problem. But you can get just as much variation here as you can with multiplication and division. You need to make sure when doing measurements that you're as precise as you possibly can be. Because like I said, if you do several versions or several calculations with those values, you can end up in a whole lot of trouble where your answer doesn't even closely relate to what other people got. And it has nothing to do with your skill. It has to do with your ability to measure. So hopefully that clarifies for many of you kind of how those rules work, how that all operates. Like I said, this is going to be something we're going to revisit over and over and over again through the whole year. If I put on your work something about you need to watch your significant digits, I'm not going to walk you through the problem on where your problem showed up, but you'll know then the problem is not in your math and it's not in your equations. It's that you started rounding wrong somewhere and it ended up in a bad place. So when you see that piece of feedback, that's what that's communicating is you didn't round properly somewhere, and now down the line, it's yielded some issues. So I'm going to take a moment and give you guys an opportunity to ask questions. I'm sure that you've got at least a few, and I know you will, going forward, I'm sure you'll come up with questions as we run across problems. It's okay if you don't have one now, but
whenever we are talking about like our tests and stuff, and if we miss a point, how do you want us to like ask a question?
Okay. You mean after it's been graded type thing?
Yeah. Do you want us to just email you?
You can either email me or you can come to the Zoom room. Some people are a little weirded out by like coming into a somewhat public forum and being like, yeah, on number 5 on, my test, I had an issue with blah, blah, blah. How did I screw that up? If it's not something like super particular, like, walk me through how to get the proper answer, email is usually just fine. The problem is if it is like, I had no idea how to do number 6, I just picked something and went with it. Then chances are we're probably going to need to work through it on like using the whiteboard here in the Zoom room, just so I can actually physically walk you through the problem so you can see this is how you get from A to B. So it kind of depends on the problem itself. If you think I just made a mistake, which happens far more frequently than I'd like to admit, then usually an email is just fine. If you ask me a question and it's going to be involved, I'll probably say something like, why don't you come to my Zoom tomorrow or this afternoon and I can walk you through it. Or you can walk me through how you got your answer. And then, we can visit about that because physics probably more so than just about any other science there are probably 4 ways to legitimately get to where you're going, just depending on your mindset and how you understood the problem, the assumptions that you made as far as like what values did you use. Because like as we saw, if you use 9.8 instead of 10 for the acceleration due to gravity, your number on the answer of your problem is going to be way different than what the answer key would necessarily have. But that doesn't mean that you did the problem wrong. It just means that you used a different value. And so sometimes we have to kind of walk through that together, because in virtual land, it can be really hard for me to follow your thinking just based off of what you type into the text box. Does that make sense?
Yeah.
Okay, so simple questions like, I think you made a mistake, happens, and just email me about it. If it's, I have no idea what I'm doing, which also sadly happens to me more than I would like to admit, then you probably want to come to the Zoom room and we can actually visit about it. Have you all been able to go back in and look at your like assignments and the feedback and your test results and things like that? Like navigating is not the problem, right?
No.
Okay. Because you guys have a different screen than I do. So that's always kind of tricky for me to like try to figure out what your screen looks like compared to mine, to navigate back in. But I had somebody ask me the other day about how to see what they missed. So I want to make sure everybody knows how to do that. Any other questions that we had? Anything else I could help you with, or? I'm sure you'll think of some later. You can always email me if you come up with some. Like I said, this is going to be a reoccurring theme that we're going to see through all of our work, starting here in this this unit that we're working on now, going through the entire year. So this will come up over and over and over again. So I'm sure that we will all get more practice with it than we like to admit. How is Unit 2 going?